spectroscopic model is the core loss modeling. So the conventional transformer model, if we want to consider the core loss, usually we'll add a resistor in parallel to the magnetizing inductor, RC there. And the assumption is that the voltage on this resistor, it represents the core loss, so that the core loss is proportional to the Vm squared. However, if we look at the core loss density curves of different magnetic materials, actually based on Stemme's equation, we know that the core loss should be proportional to the betas of the Vm. So these two are not equal to each other, especially when beta does not equal 2, which is the case for most magnetic materials that has a beta larger than 2. So the problem is that if we use a fixed RC value for different current excitations, the traditional model gives us a very large error in terms of predicting core loss, because core loss is nonlinear, and we have to readjust the value for RC under different current excitations. And also, if we look at the time domain waveform on that resistor, it gives the wrong shape. In order to solve this problem, we developed a sub-circuit model for time domain core loss. I'm not going to go too much detail on there. This picture just shows the sub-circuit we developed. Actually, the input is the primary current and the secondary current. And then we will use some material properties as the input, together with a geometrical related factor to represent the field effect on the core loss. And what this model does is that it gives us a dynamic core loss that can be feedback to the converter to interact with the simulation. And also this model is good for arbitrary excitations. No matter how you change the current excitation, this model just gives you the time domain core loss. And also it takes into account the geometry related non-uniform field distribution considerations. The modeling result of core loss is that we can pack the subcircuit into a box, and then we use the primary current, secondary current as the inputs to the box, and these core loss simulated are feedback to the main model in terms of variable resistors. So that for an arbitrary current excitation, we can simulate the core loss pretty accurately in the time domain, so that we can track how does the core loss changes when the input current changes. And also for the nonlinear core loss, we are able to capture the core loss changing with current excitation level without the need to readjust the parameters values.
One question I have is, so what is the basic assumption here? Like when you use Maxwell, right? I guess you assume that is accurate.
Yes.
Yeah. So for Maxwell, how do you actually model core loss there for arbitrary current waveform?
Right. In Maxwell used a time domain core loss model, and what we do is we use the same model but implement it in circuit solver. So that's why we are trying to compare with Maxwell. And the benefit for using Maxwell's model is that Maxwell has this field distribution information, and also it has, together with this core loss model, it gives us the time domain core loss. The methodology used there is to calculate the hysteresis of the material for a dynamic minor loop. So when the current excitation changes, it doesn't have to be a periodical waveform, but it can be a transient waveform. and it's based on calculating the area of the minor loops to get the core loss. So
in Maxwell.
yes, and also for the SPICE model we developed, they use the same model.
Okay. So how does this compare with, for example, you showed GSE, IGSE, those methods?
Yeah, the major difference is that this is a time domain method. And actually it's the, as far as I know, the only method that gives the dynamic time domain core loss predictions. All the IGSE, MSE, they are frequency domain solutions, which requires, like, for example, you know the period of your excitation, and you can calculate an effective or equivalent frequency of your excitation, and it gives you an average core loss. That is not applicable in our case because we want to feedback this dynamic core loss simultaneously as the simulation runs. So that's why we need this time domain model. To summarize the macroscopic model, we have developed a methodology to calculate the field distribution with non-uniform flux density, and that helps us to calculate all these parameters here. And also we use separate neutral inductors based on the flux density distribution. And also we add winding loss resistors to include the phase shift impact to make it more complete. And we use this time domain variable resistors to feedback the core loss information into the main model. And this model is ready to be plugged into converter level simulations. This helps us to deal with the three challenges we mentioned earlier. Then how about the other challenges like pH saturations and the frequency dependency? There are actually also existing methods in power electronics that we can just add this paralleling networks to include the frequency dependency, and we can also add a switch there representing when the inductor saturates, that is the saturated value of your inductor. But this requires massive curve fitting networks. Basically, you just measure as much results as possible, and then you use these components, these paralleling networks, to trying to fit into those measurement results. It has become a brute force methodology. And the bottleneck of this method is that it uses a top-down solution, which means we first observe a behavior and we do some approximations on the pattern, and we use some models just to fit that behavior. And this will reach a dead end when it comes to a very complex condition. What about if measurement is not possible, or if the magnetic material's property is just dynamically changing? So how about we switch the direction? How about we go bottom-up solution? In the bottom-up solution, we start with microscopic theory, and then we can find an equivalent model to model the micro-scale magnetics. And then it helps us to simulate the pattern and helps us to predict the outside behavior in the microscopic scale. So if this method works, nothing is fitted, no more curve fitting. We can just use the fundamental physics to predict the outside behavior of magnetic components. Then this slide shows some understandings of the let's try to understand what happens in the micro world. So like I mentioned earlier, this spinning electrons or magnetic spin, it has a magnetic dipole moment m inside the material, and the flux density B comes from the superposition of the external H and the internal magnetic dipole moment m. When an external current generates an external H, this H will force these magnetic spins to realign and rotate. And this famous equation describes the rotational motion of these spins, which is called the LLG equation. It actually just gives you how does H changes M inside the material. And this actually is the answer why we have a nonlinear BH curve. For basically, when the external H is large enough, these magnetic spins, they can no longer be aligned. There's no more spins to align, and the rotational behavior stops. So that's why we see a saturated behavior. And also this helps us to understand the frequency-dependent permeability of magnetic material, which means when the frequency of the external H is such that it is equal to the self-resonance of the spins, then the magnetic material has a self-resonance behavior that gives a frequency-dependent permeability of mu prime and mu double prime, where at the resonance, mu prime, which is the permeability, drops to 0, and the loss, mu double prime, reaches its peak. So this confirms our bottom-up solution that we can use some micro-domain behaviors to predict the nonlinearity and frequency-dependent performance. Currently, the micromagnetics are practically used in RF area. For example, this shows a circulator that uses magnetic material in the RF area. It uses an anisotropy behavior, which means the spin has a rotation direction. So the signal coming from different directions, they will see different permeabilities because of the magnetic spin has its own trajectory and direction. Another application is the frequency selective limiter, which uses the nonlinearity from the magnetic material, which means if there is a small signal going through the device, it receives no attenuation. But if a large signal going through this device, it receives a larger attenuation, so it becomes cut off. And the frequency selective behavior is from the frequency dependency of the permeability, which means if the two signals going through the device together, only the large signal will be attenuated. And also in RF domain, there are some material simulators, but these material simulators, they are in the nanometer scale, which is not possible to use for even RF devices. They're in micrometer or millimeter range. And there is no existing model that can model this nonlinearity behavior from the magnetic material. What we need to solve is to solve the drastic material to component scale disparity, which means how can we apply the material's property to a component level. So we start with modeling a single magnetic spin. So this picture shows the simplified trajectory of magnetic spin in thin film magnetic materials. And this equation describes the motion of the spin. We found it very similar to a mechanical system, where a pendulum just swinging around a fixed point. And this is the equation describing this pendulum system equation of motion. And connecting these two domains, we found one-to-one correspondence regarding the magnetization in the magnetic domain actually is equivalent to the length of the oscillation. And the magnetic field becomes the gravity acceleration inserted on a swinging object. And the vacuum permeability is actually the mass of this pendulum. And we know that for a mechanical system, especially a pendulum system, we can use a second-order circuit to model this behavior. And if we connect these two domains together from the mechanical to circuit domain, we can also find a one-to-one correspondence between these parameters, like the voltage across this resonant tank. This actually means the magnetization in the magnetic domain. Current going through the resonant tank actually is the magnetic field. And the vacuum permeability is the initial inductance of this of the resonant circuit. And actually the energy stored by the capacitor means the kinetic energy in the mechanical system. The energy on the inductance means the potential energy from the mechanical system. And the loss on the resistor means the friction loss of that swinging system. And since for magnetic spins or for the pendulum, it includes two directional oscillations, one along x and one along y. So that's why we use two resonant tanks to represent these two oscillations, and they should be coupled to each other to represent exactly what is in the pendulum system. So this circuit model helps us to describe the magnetic motion in the microdomain. And in order to model a larger scale of the device, we know that inside the magnetic material, the spin, they don't have a uniform direction. There are some phase shift between different spins. And this phase shift between the motion is introduced by exchange coupling between the spins. And by doing some derivations and calculations, we can add that exchange coupling to the circuit model in terms of a coupling inductor, so that we have this coupling between spin and spin to model this large-scale performance inside the magnetic material. And this circuit model actually gives us a very good prediction of the frequency dependency in terms of the resonance of permeability, both from the real part and the imaginary part, which validates our assumption that we can use this macro domain circuit model for some large-scale performance simulation. And we validate this model with an RF application in frequency selective limiter. On FSL, usually it has a microstrip structure, and the RF signal goes through the microstrip. It generates an EM wave, and this EM wave will generate some spin waves, or you can think of it as another type of magnetic energy taken away by the magnetic material. And this coupling between these two gives us the nonlinearity and the frequency dependency behavior. And our model, compared to the measured results on a real device, shows that it has successfully predicts the nonlinearity. Like, for example, when the input power increases, it shows a larger attenuation to the input power, and also it has this strong resonance at a certain frequency because of the self-resonance of the magnetic material. To summarize my work, I start with component level modeling. Includes like magnetic field, inductance, winding loss, core loss, etc. this is for behavioral modeling. And then I go to the material level to extend my knowledge to micromagnetics and magnetic spin models, so that they can be integrated to larger scale simulations. And this completes our understanding in the materials and the components level modeling method. Like we mentioned earlier, any in-depth modeling and understanding here should be able to benefit us for the top-level designs. Then how these models we developed for magnetics is going to contribute to these areas, what the models can do. I will discuss some applications based on these models. Some of them are my past experience, and some of them are my future plans. So it's a mixture of both, but it shows the capability of these modeling methods. First of all, an application is that we can come up with a constant flux inductor, which means we can manipulate the distribution of current density inside the magnetic material to achieve a programmable field distribution. For example, if we have a uniform field distribution, then we can greatly reduce the size of a magnetic component. And this picture shows the fabricated prototype compared to a commercial counterpart with similar ratings. And it shows a 2 times reduction of the volume. And this picture shows this inductor hat made with LTCC core. This research was sponsored by NSF, and Dr. G.Q. Liu's research group, they have been actively working on 3D printing of this structure, because this is a structure that is not so easy to achieve with conventional manufacturing methods, but it shows a great advantage for doing so. So they're using 3D printing to print the irregular shape of the core, of the winding, and also they use some low temperature cured magnetic materials to mold this inductor. Then by doing this, they are able to fabricate very small size constant flux inductors. And there are some ongoing research on this.
So on this one, I suppose it's mostly coming from the way geometry was
Yes.
designed.
Mm-hmm.
So how is this related? How is this related to the modeling part?
Okay, the modeling part actually gives us the tool to generate what we want from the component level. Like for example, we can model how much current density gives how much flux density, and then we have a way or a tool to get a uniform field distribution, for example. Then we know how to design it. How should we place the current density?
Could they use other tools or even analytical model you mentioned at the very beginning to come up maybe with the same design?
Well, we can use softwares like Maxwell to run optimization sweeping methods, but that is like just we sweep parameters, a lot of parameters to sweep and to get the best design. But from our modeling tool, we have the strategy. We not only for uniform field distribution, but for example, if we want to have canceled flux coming through different current density distributions, we're also able to do that with the modeling tools for the field.
So your tool is essentially based on analytical model, but you implement it as an easy to use tool.
Right,
to
right,
summarize
right.
that.
We can use it for different purpose. Another application is in the wireless power transfer. Remember that we had this modeling methods for planar magnetics. If we just increase the scale, and it eventually becomes a wireless power transfer coil. Like this is the transmitting coil for the top core plates and the bottom receiving coil from the bottom core plates. And I know that wireless power transfer, it has a lot of requirements on coil design, especially regarding the stray magnetic fields. And we have a modeling tool. We have a modeling tool to address this fringing flux issues, so that we can apply the same methodology but to a different scale to make it applicable to wireless power transfer. Another application is that we can use multifunctional material for packaging. For example, this is a project funded by NSF. Traditional power module, like point of load converters, it not only includes an inductor, but also it comes with a molded case as to encapsulate everything inside. But if we can use the magnetic material as an encapsulate material, so that everything is molded by the magnetic material, then we can save the volume significantly. But this also comes with a lot of problems when it comes to like increased parasitics, because everything now is surrounded by magnetic materials. We can also do some study on the impact of parasitics, and also we need to redesign these wire bonding connections to minimize the impact, and also the thermal performance of this magnetic material, whether it can be used as an encapsulant, that is a problem to look at. Another application is that packaging with magnetics. This work is done by my colleague Zichen Miao at Virginia Tech. And what he does is that he packed a negatively coupled inductor into his power module to solve the imbalance of the transient current with paralleling devices. So this negatively coupled inductor, it's made of PCB windings, and also it's LTCC core. This shows a direction that maybe for some packaging related topics we can use magnetic materials to partially solve these issues coming from active devices. And then in this case, we will need to worry about a very high frequency analysis, because for the transient current, it includes this very high, several tens of megahertz information. And also we will need to analyze the frequency dependent dynamics, and how do we select the materials that is suitable for high frequencies.
Can you finish in 5 minutes?
Yeah. Okay. Last application is for a magnetic antenna for ultra-low frequency emission. So this one actually used a similar concept of the pendulum, but we use a permanent magnet. Each of them is permanent magnet, and it's like a scaled up phenomenon of the magnetic spins. And when there is an RF field applied to this pendulum system, it emits EM field into the air. And this one actually use the same model that I developed for the magnetic spin, so that this physics, although the frequency is a lot different, but the physics connects them together. So other potential applications based on the modeling tools that includes EMI filters. We can have frequency selective materials designed for EMI filters, and a popular direction is to go heterogeneous integration. We can try to choose magnetic materials that is good for integration. And for wide bandgap applications, there is some high frequency magnetic design problems, and there are EMI containment concerns that we can use these modeling tools to address. And lastly, an e-mobility system that where high temperature evaluation and whether the magnetic material can survive under a high temperature, that is also something interesting to look at. And in a word, the magnetics stimulates versatile innovations in the electronics world. So I'm very excited about this field, and I think it's a promising field that not only contributes to power electronics or RF, but also for a wide range of frequency applications. And I'm also excited to share my knowledge to the students. I look at the curriculum of the ECE department that I found some existing courses that I can teach, like field-related courses, electronic circuits, electromagnetics, and microwave circuits. And of course, power electronics related classes like PE and PE circuits, high frequency power electronics. And based on my magnetic background, I would also like to introduce some new courses to the department. For undergraduate level, it could be magnetism and magnetic materials and applications in the engineering world. I can talk about, this is actually a cross-disciplinary course that material science department students and ECE department students, they are all welcome to attend. They can learn how some fundamental physics of materials and their applications in the electronics world. And also for graduate level, I can develop some courses on inductors and transformer designs for PE and high frequency magnetic components. These helps the power electronics graduate students to get more knowledge about the most advanced technologies in magnetics. I think it will be a useful addition to the existing curriculum. So my goal is that I want to share the cutting edge technology and inspire students with groundbreaking ideas, and especially for the underrepresented groups. And my hope is that I can create a very friendly and welcoming environment for the students to pursue their passion, and I will just support them all the way. And that completes my presentation, and thank you everyone for attending my presentation. Thank you for the opportunity for this conference.
We're running late, but I think we can still take a few questions. Or let the faculty, the faculty members give you priority.
You have any interest in motors, motor design?
Like I said, I have a magnetic background, and I don't want to limit it to a special application. So as long as it is an application that is related to magnetics, then there will be some interesting topics to look at. So if the motors, they require better understanding or an optimization of the magnetics part, I have interest in working on that area.
Question is for your modeling. Do you establish model in the 1D dimension or 3D dimension?
It's right now it's like a 2D dimensional. 2D-dimensional.
2D-dimensional.
Yes, assuming it's like a rotational system. It has a rotational Z, and it rotates around the Z. So it assumes the variance along the Z direction and the R direction, but not along this phi direction.
Okay. Okay. I see.
How do you verify your time domain core loss model in experiment?
Well, in experiment, it's hard to verify because right now we don't have very good measurement techniques for time domain core loss. We don't even with the most simple case with sinusoidal excitations, it's hard to get the accurate core loss measurement. So right now it's only verified by finite element analysis.
Okay, if no other questions, then please join me in thanking Dr. Helen. The next half an hour.
Next door.
Next door.
4:30.
Can someone solve the video?
You use the
Which one? Yeah, where's the record button? Is on your side.
Oh, is this one on though? I don't know. There is a button here.
Yeah, there should be a button.
I mean,
Oh, yeah.
every circuit.
Oh, start.